Welcome back to Calculus 1. We are in section 2.3. It's about limit laws. And basically, according to those limit laws, they do allow us to calculate a limit using the so-called direct substitution. And also, we figured out there are cases that direct substitution cannot be applied. So the trick we just considered, it is to consider factorization. Like here and there, and the other examples, we figure out we can do the factorization for the numerator, or for the numerator and the denominator both. After doing the factorization, somewhat we can cancel the factor generating zero. That is really the thing about factorization. We want to cancel the zero factor from the denominator. And if that indeed happens, then we can use the direct substitution. And all the examples we just finished, they are all about factorization and direct substitution. Again, it is true to find our limit. That is really the only way to find our limit, precisely, the direct substitution. If the direct substitution may not happen, and we do some tricks, we manipulate the limit and to make the direct substitution happen. And so let's take a little more examples. This part, it is example 2.8 from the textbook, and 2.18, I'm sorry. And indeed, as you can tell, the direct substitution really, it's not going to work. It's not going to work, right? If I replace x with -1 and -1 plus 1, that denominator is 0. And also, interesting enough, usually when you get to the situation denominator 0 and the numerator 0 too, it's just true in this case, numerator 0 if you do a direct substitution for the numerator. So indeed, it is the so-called indeterminate form, 0 over 0. We call it indeterminate because it could be of anything. It could be of anything, okay. So this case, well, I want to say factoring may not work well at all, right? Even though if you work very hard, there could be some factorization from x plus 1. And then how do we really do the factorization for that square root? I have no clue. And speaking of square root, you may want to know a mathematical concept. It is called as a conjugate pair. In general, if you have two terms, a plus b and a minus b, together they form a conjugate pair. And also we did review some formulas in chapter 1, algebra formulas. And in particular, I want to know if we multiply the conjugate pair together, it will generate a formula of difference of two squares. And then, especially if we are having radicals, square root. Okay, when you have a square root of squared, it will take away, it will cancel. The square root will be canceled. The square root will vanish. So it is very helpful, okay. Besides factorization, when you have numerator denominator with square root, you want to consider use its conjugate, because the product of the conjugate pair is the difference of two squares. There is a good chance the square root will vanish. And also another small issue you may want to know here is when we manipulate a fraction, you want to keep the fraction in the original form, right? The equivalent form. So you always do the same thing for numerator and the denominator, okay? So this is what I did for the limit over here. I did realize it's not possible to consider direct substitution, but as I explained, I'm seeing a radical term, so I consider the radical conjugate. The radical conjugate, which is square root of x plus 2 plus 1. So I multiply the radical term by its conjugate, and it turns out to be the difference of two squares, right? And square root of x plus 2 squared, it's just x plus 2. Certainly 1 squared, it is just 1. So the product of this conjugate pair seemingly may be complicated, but it does reduce to x plus 1. Okay, this is the first part, and then I'm saying work with this limit. I really need to manipulate this entire fraction. And to manipulate a fraction, you do the same thing for the numerator and the denominator. So I multiply the numerator by its conjugate. Then I multiply the same conjugate to the denominator. Certainly, well, that is the same. We keep this fraction balanced and in the equivalent form. Certainly, you can cancel the conjugates right now. But anyway, that's nothing, right? That will go back to the original form. So we do not cancel the conjugates. Okay, we look at the numerator and the denominator separately. For the numerator, I have the calculation part done over here. So the product of this conjugate pair for the numerator, it just tends to be x plus 1. Then for the denominator part, you really don't want to do anything in a rush. Keep the denominator untouched. And then one thing I just realized. The numerator, now it is a factor of the denominator, right? So x plus 1 is cancelled. So the limit of this original problem turns out to be the limit of this new one. For this new one, did we say to calculate the limit, we consider direct substitution? There's no issue with direct substitution, right? Replace x with 1, negative 1, I'm sorry. Replace x with negative 1, it turns to be negative 1 plus 2. So that's a square root of 1. Square root of 1, that's 1. 1 plus 1, that's 1. So in the end, the limit, it is just 1/2. Might be a little hard starting such a weird thing, and then we get to the limit as 1/2. Okay, essentially it is still about direct substitution, but it is in the situation direct substitution may not work. So this time what we consider here, it is using the conjugate. And you must know this formula very well. Now I want to present or call this formula in a different way. The product of a conjugate pair, it is difference of squares. Okay. One more, I think this is also from the textbook, checkpoint 2.14. And this limit, you cannot use direct substitution. Replace x with 5, it's a 0. And again, interesting enough, numerator is 0 too. 5 minus 1, that's 4. Square root of 4, that's 2. 2 minus 2, that's 0. Okay, it is in the indeterminate form of 0 over 0. And then, because of the square root, I simply multiply the numerator by its conjugate. And also because really I'm considering this entire fraction, I did exactly the same thing to the denominator. Then the numerator turns out to be the product of a conjugate pair, which turns out to be the difference of perfect squares. Difference of squares. Square root of x minus 1 squared, that's x minus 1, right? 2 squared, that's 4. So the numerator, indeed, it is just x minus 5. Then for the denominator part, usually, this is just true when you manipulate fraction, you're focusing on the numerator, then don't do anything for the denominator. Or if the other round, if you are working on the denominator, don't do anything for the numerator. Okay, so now at the moment, don't rush to do anything for the denominator. And then surprisingly, I'm just seeing this is x minus 5. It is a factor of the denominator, right? X minus 5 is cancelled. Okay, and also this part, it should be x approaching to 5. Let me make the update. X approaching to 5. After cancellation, I hope you see there's no issue to consider that so-called direct substitution, right? Replace x with 5. That's a 4. Square root of 4, that's 2. 2 plus 2, again, it is a 4. So finally, I got the limit as 1/4. Limit as 1/4. So again, this part, it is about using direct substitution to find out a limit. And so far, we covered 2 extreme cases. We cannot use direct substitution directly because the limit, it is in the fashion of indeterminate form, 0 over 0. Then we consider factorization. The second case, we just finished in this part of the video, when we have a radical involved. So most likely factorization may not work, but with radicals, usually you want to consider the radical conjugate. And you need to know this formula very well. The product of a conjugate pair is difference of squares. Especially with those squares, they will help cancel the radical notation. It does cancel the radical notation. We did 2 of them. So thank you for watching.